The final application example that I want to go through here is, again, work that was just recently published, and I will include the paper citation if you're interested in learning more. But for this study, Massbox characterized a multi-material, additively manufactured stainless steel 316L to Inconel 718 material. So if you're not familiar with multi-material additive manufacturing, this technology has a lot of potential to allow engineers and scientists to spatially design parts that will meet the increasing demands of industries like aerospace, for example, for more extreme environments and improved performance. So essentially what this allows you to do is actually vary chemical composition or microstructure or mechanical properties spatially within a part so that you can strategically strengthen or improve certain areas and then leave other areas with maybe a metal alloy that's not as heavy or less expensive. And so that's exactly what these researchers at Ohio State University did. They went through a pretty rigorous design process of creating this notch-strengthened tensile bars that used stainless steel 316L in the grips and then strengthened the notch with an Inconel 718. If you're not familiar with that term, that's a nickel super alloy and has some pretty, it has some really good mechanical properties, but it is more costly and heavier than something like a stainless steel. So you can see how it's used only in the notch where that part needs to be strong. This was done through directed energy deposit, or DED, printing process that uses powder and a laser process to deposit. And essentially what was done is from the bottom up, we've gone through layer upon layer of stainless steel, then switching to that nickel superalloy, then switching back to stainless steel in the build process. And the challenge here is that that interface between those two materials is critical to design properly, because anytime you have two materials that have different properties, different thermal properties especially, that can potentially be a weak point, and that can potentially be where defects occur. And so what was done in this study is a range of different characterization tools, as well as mechanical testing, in order to determine if this type of multi-material additive manufacturing process was viable to meet some of the increasing demands of industries. So what we're looking at, so what I'm going to show is just a series of figures that are pulled, again, directly from the paper that was recently published. I will include that full citation, so you're welcome to go and take a look at it yourself. But first, we're going to look at some optical microscopy images. So first, these tensile bars were ground, polished, and then etched so that the different materials were obvious in this optical microscopy view that you're looking at here. I'll point out that this was before any sort of mechanical testing was done. So this is just the tensile bar before it was broken. And what you can immediately see is these kind of curved patterns here that represent the melt pool beads. So as the DED printing process is moving from one layer of stainless steel to one layer of nickel alloy, the laser melts a specific area and creates this melt pool. And there's a process of Marangoni flow that creates these swirls that you see, especially in the upper interface here, where we kind of see these defects or areas where there's these swirl patterns where the material was not completely mixed after the material was switched. So we're able to see this with optical microscopy. But then what Massbox allows us to do is actually determine the chemistry of this interface as well as these swirls. So what you're looking at here, Massbox analyzed an area essentially over that top part of the stainless steel to nickel interface. And if we look at the iron map, we can very clearly see we've got this area that's purely 316L, we've got high iron, we've got this area with low iron, that's the Inconel 718, but this interface area is an area of mixed chemistry, where you see a very steep gradient on the iron map compared to less of a steep gradient on the nickel map, kind of as we're changing from nickel to stainless steel. And again, you see those that segregation or those swirl patterns where we have low iron, we have low manganese, we have low chromium. So essentially we have low amounts of all of those major elements that are in the 316L. We can also see kind of the diameter of these melt pool beads and compare those with the laser parameters that we used. But the other piece to point out here is what the researchers highlighted on the chromium map, which was kind of these bands of compositional gradients. And so what they hypothesized is this might suggest that there were some lathe structures being formed in this process. And so then what they did was take a look with SEM and combine it with EDS. So doing a microstructural analysis with SEM, in the first couple of panes looking kind of down on the build direction, and then in these panes looking parallel to the build direction, so similar to the view that you have here with the mass box maps. Again, looking on a much smaller scale with the SEM on that microstructure and grain scale, and able to point out that, yes, in fact, there do seem to be these lathes strips, and interpreting them as a segregation of molybdenum and chromium. So this is, again, just an excellent representation of how mass boxes, broad scale elemental maps with micron resolution complement the microstructure and grain scale understanding that something like a SEM-EDS gives you. You can see, you can map across multi-material interfaces and then use a higher sensitivity or, sorry, higher resolution tool like SEM-EDS to go and look at some of the microstructure and grain level heterogeneity. And they're both corroborating one another. So the final slide on this study is, this shows the graphical abstract from the paper and then includes the DOI if you want to go and look this up. But I dove into a lot of details on the characterization. But one thing I want to point out, if we take a step back to the overall findings of this study, is that overall this was a success. You can see that the researchers did successfully create significantly stronger tensile bars by doing this multi-material additive manufacturing process. They showed 40% greater strength when doing tests at room temperature and over 100% greater strength when doing this at elevated temperature. And what you can see over here with the 3D digital image correlation coloring the first principal strain here, these was essentially, this image was collected while the tensile test was occurring, is that even though there was compressive stress occurring at that interface, because of the thermal expansion mismatch, then it actually kept that interface intact and allowed the notch to be the weak point. And so essentially these tensile bars did fail where they were intended to fail. And this finite element analysis is really critical in kind of explaining why. So, you know, overall, great work by the researchers creating these not strengthened tensile bars, demonstrating that multi-material additive manufacturing can create parts with significant strength compared to parts with just a single alloy. But what these different characterization tools showed across the interface is that there is room for improvement. There's room to further optimize printing parameters and kind of what happens at that interface so that we aren't seeing as much of that segregation. Maybe we aren't seeing some of those lathe structures that we identified with the SEM-EDS. So that was certainly one of the key takeaways. And again, just shows you how mass boxes, elemental maps can be used in conjunction with many other characterization tools to advance the work of multi-material and advanced manufacturing. But then the final piece here, just to show something that's easier to show in video rather than in static images in the paper, is what we did with a three-dimensional analysis. So I'm going to play this video and just show you that we analyzed an area across that 316L stainless nickel alloy interface. And then we did a specific analysis right on one of those melt pool beads. So you can see we did an analysis on the melt pool bead, but then repeated that analysis so that we were getting a 10 micron deep depth profile. So again, essentially what we did was just with those elemental maps, repeated that elemental mapping process, ablating away hundreds of nanometers in this case per layer, so that we created a depth of 10 microns that was validated with a microscope measurement. And then because each one of these voxels contains that full mass spectrum of data, we're able to look at all of these different elements that we detected and see, are they concentrated in the steel or the nickel side? Are we seeing them in the melt pool in that area of mixed chemistry? Are there changes from surface to subsurface? And gives us a much more thorough examination than just the surface analysis alone. So now that I've just kind of oriented you on the video, I am going to let it play again so that we can look at some of those elements in a little bit more detail. So once again, took the tensile bar sample, analyzed the 316L to Inconel 718 interface. From an elemental map, we were able to determine exactly where we should analyze in order to profile through one of those melt pool beads. By doing 20 layers of analysis, we corroborated that with a microscope that we removed about 10 microns of material. And now we can look at all of these different elements. So for example, manganese, which is higher in the steel, we see was a big part of the mixed chemistry area. Aluminum was as well. So it's primarily concentrated in the nickel, but we do see a decent amount of aluminum in that mixed chemistry in that melt pool bead. Niobium is also a major component of the nickel alloy, but we see that into the mixed chemistry area. Molybdenum, less so. It's more concentrated in the steel. Cobalt was interesting because it was primarily subsurface and wasn't as much on the surface. Chromium showed the opposite trend, where it was more concentrated in the mixed chemistry area on the surface and less so subsurface. And then vanadium was a trace element that was primarily identified in the steel and not as much in the melt pool or the mixed chemistry area. And there's just once again a look at that iron versus nickel, so the steel versus Inconel.